in problem number 4, we have two congruent isosceles triangles, A, B, C, and D, E, F, and they overlap so that their bases are parallel and the vertex of each is the midpoint of the base of the other shown. Alright, well, let's make sure we understand what all that means. There's a lot of mathematical terms here, so let's go through them. Okay, so first of all we have a congruent. Now congruent just means that the triangles are the same shape and size, which would tell you that all the angles are equal and all the side lengths are equal. Okay, so A, B, C, and D, E, F are congruent, so the same shape and size. They aren't oriented the same, obviously. You know, one is sort of inverted 180 degrees from the other one. And but they're congruent. They're still congruent because of the same shape and size. We're also told that these triangles are isosceles. And isosceles means that two of the side lengths are the same. Okay, and in this one you can kind of see it looks like AB and AC are the same side length, right? And for DEF it looks like DE and DF are the same side length. And since they're congruent, then DE, DF, AB, and AC are all the same length. Okay? And they overlap so that the vertex is the midpoint of the base of the other. Okay, so here's the vertex of A, and we're told that it's the midpoint of the base of the other one. Okay, so the base is EF, and so the point A divides EF into 2. So we could actually mark that on here, that this length and this length are the same, okay, because it's the midpoint. And the same way down here, this point D is the midpoint of BC, so we could say that this length and this length are the same. And because these triangles are congruent to each other, then all four of those lengths, AE, AF, BD, and DC, are all the same length. Okay? So, let's see. Oh, I don't know if I mentioned too that these are isosceles triangles. They have the same side length, but it also means that the angles are the same. The angles that are opposite the equal sides are equal as well. So we could mark that here and here. So in an isosceles triangle, this angle E and this angle F have to be equal if the side lengths are equal. In the same way down here, angle B and angle C have to be equal, and they all equal each other because the two triangles are congruent. And also because they're congruent, this angle up here, angle A on the triangle ABC, so it's the vertex, or this, what do they call it? Yeah, it's this vertex at A is the same as this vertex at D, okay? Those are the same angle. Now I marked those with 2 arcs instead of 1 because they aren't necessarily the same as these other angles at EF and BC. If they were, they'd be 2 equilateral triangles, but it doesn't say they're equilateral, it just says they're isosceles. And equilateral is just a special case of isosceles where all the side lengths and all the angles are equal. But we don't have that information. So I just marked that with 2 marks instead of 1 to indicate that that is it's not the same angle as the one marked with 1. Alright, so what else are we given? If the area of the overlap is 12 centimeters, how many square centimeters are in the area of triangle ABC? Okay, so we're given that this shaded area is 12 centimeters. And if you look at it, I could actually divide this figure in 2, right? And you could probably guess that all of these triangles, this, you know, these white triangles at the edges and the 2 shaded triangles that are part of this parallelogram in the middle, they look like they would be congruent, and you would be right. And so if that's the case, and this whole shaded region is 12, then this has to be 6. And this has to be 6. And if all of these smaller triangles are congruent, then this would have to be 6, and this would have to be 6. And we're asked to find the area of ABC, so it looks like we have 6 plus 6 plus 6 plus 6, which is 4 times 6, so that's 24 square centimeters. And that actually is the answer. Okay, a lot of these problems have to do with dividing the shape up into congruent shapes. So in this case, we can divide it into 6 congruent triangles, and then ABC covers 4 of those triangles. Okay, it's a little more work to actually prove that all these triangles are congruent, but it's not too bad. We're given that these lines here are parallel, EF and BC. So you can see that we have 2 parallel lines that are crossed by a third line here, this DE line. And we know from geometry that the alternate interior angles are equal. Okay, so we know by the fact that these are alternate interior angles of parallel lines that this angle here and this angle here have to be equal. And we can also see that then we have this parallel line BC and this one at EF, and there's a line going from C to A that intersects both of them. So this is also an alternate interior angle to this one. So those angles are the same. And it looks like we could also mark this one because, again, this AB is intersecting 2 parallel lines. So this angle and this angle down here at B are alternate interior angles, so those have to be the same angle, right? And then we have a little theorem called the angle-side angle theorem, which says that if you have 2 angles and that are the same and the side between them is the same, then those triangles are congruent. Okay, so they often call it ASA, so angle side angle. So you have 2 angles and a side between them, and if they are all equal to each other, then we know that, let me see if I can mark it here. We know that this triangle here, I don't know if yellow is the best color to use here, but in this triangle here, and this triangle down here, and this triangle down here have to be congruent by the angle side angle theorem. Okay, we have 2 angles and a side between them that are all equal. And we also know, look, you can also tell these are actually isosceles triangles, right? Because you have 2 angles that are the same, which means that the sides opposite those angles have to be the same. So this side and this side are equal, and this side and this side are equal, and this side and this side are equal, this side and this side are equal. And so what else can we figure out? Okay, here we have a side and an angle between the 2 sides. And here we have 2 equal sides and an angle between the 2 sides, okay, and inside the shaded region, okay? So there's actually another theorem that says, it's the SAS theorem, that the side angle side theorem, that if you have two sides that are equal and the angle between them is equal, then these triangles are congruent to each other, right? So we know those are congruent. All right. So can we show that those pink triangles and those yellow triangles are all congruent? Well, it sure looks like it, doesn't it? So let's see, how can we do that? We can, we have the sides are equal, right? We have this side and this side are equal. And let's see, I guess, um, what else can we show here? I'm sure it's obvious to you. So, let's see. I think we can probably show by, if this is a parallel line across here, we can probably show that this angle has to be the same as this angle, and this angle has to be the same as this angle, and what else? I think we showed this one as already equal. So this angle and this angle have to be the same, and this angle and this angle have to be the same. So we've got equal angles, equal sides. So all of these triangles are congruent. So that takes a little longer to show that all the triangles are congruent. And you probably wouldn't need to do that on, when you're in the middle of a contest exam. You would be able to just say, okay, these are definitely congruent, just by inspection. And you can see that if we add up all of those congruent sizes, then we get 24 square centimeters.